Hello, my name is Aleksey Shvedyuk. I'm a software engineer. I want to talk about my contribution to a project. At the first, I will describe the product. At the rest of the time, I will talk about problems I had solved. I combined the problems in groups. Machine learning problems, difficulties with launching the video process handling on a single board computer, monitoring, accessing, and deploying to the devices, architecture solution for fast and flexible report system. The project provides emotion recognition technology. I will talk about how it works. Here is a photo from a pizzeria. You may see the webcam, the customer in the frame. There is a single board computer doing all the computation right beside the service location. The device finds faces and recognizes emotions. The device only sends out the metadata over the internet. Sometimes the connection can be very expensive to send the entire videos. The screen shows the client's emotions metric, and staff can benefit from that information. It has the same effect as a pedometer to make you fit, computation and gamification. The UI allows you to build up a report with this data. You can compare your employee results within an interval and location. Let's talk about ML problems. The emotion recognition process begins with finding faces on each frame. A pre-trained convolutional neural network was taken to recognize one of the 7 base emotions on an input picture: anger, fear, disgust, happiness, surprise, sadness, and neutral. But the picture should contain just a face. In order to achieve that, we need to find all the faces and crop them out of the frame. I processed a lot of pre-recorded videos from the places the device are supposed to be, and got data such as angles, light, and distance from the camera to the people. A data set was generated in semi-automatic mode to check face detection quality. The face recognition model was a bottleneck, so I took the processing speed into account. HOG model from the LEAP tool was chosen in the result. Now faces can be used as an input for the emotion recognition model. This method isn't sensitive to the order of source frames, therefore the results are unclear. In essence, on one frame, the face was interpreted like surprise. On the second frame, could be interpreted like neutral, and the third could be recognized like fear or sadness. This information wasn't useful. I could understand the business need. It was crucial to get clear results in order to make successful sales of the pilot. Otherwise, our clients were confused by emotion interpretation. To solve this issue, I created a model which determined the mood as a continuous value changing with time. Basically, there are 3 moods: positive, neutral, and negative.
An assumption was made that commonly humans can change the mood in a half-second interval. A model was trained by using the dataset which I described before. In the result, the model shows what happens with the human mood exceptionally well. We name it a trend of mood, or the trend. After that, it was pretty easy to calculate the amount of different trends per day, staff, shift, etc. Unfortunately, the trend only works when there is a single human in the frame. Otherwise, we will get a single trend for everybody in the frame. The problem is that we need to sort faces by groups. Each group should have the face images of only one person adjacent by time. One person can be in few groups, but each group should contain face of only one person. Also, it's necessary not to decrease the performance. I solved the problem by calculating overlap of face area on adjacent frames. Now the trend could be computed for the face within a single group, and it produced correct result. Still, one human can create several groups if he goes out from the frame for more than a few seconds. It doesn't influence the trend, but this problem was solved too. There was a lot of time without anybody in the frame, within each implemented places. It was an idle time. I used this time to calculate a vector of facial features in each frame. Performance didn't change since these computations were made during the idle time only. We can compare pairs of vectors and understand which faces are more similar. The model used the following artifacts: a vector of faces features, a distribution of face by groups, facts about all the faces located within a single frame. And the result, this method united the closest groups very good. Let's talk about the difficulties of launching the video process handling on a single board computer. The startup principle required us to focus on checking business hypotheses as fast as possible. Therefore, all our efforts were aimed at delivering the valuable features first. At first, the architecture wasn't optimized to run on a single board computer. But then we encountered the demand to run our product on the embedded devices. So I had to do my best to adapt the design within the strict time constraints. These constraints dictate the ways and solution for the task at hand. I want to talk in depth about the device choice criteria, but I will describe the libraries running on the device. I just want to say that the reason for this choice and other restrictions were explained by the values of these parameters. I want to say more about the performance estimation. Due to the specifics of the Picket libraries, in particular parallelization of computations, it was necessary to compare the performance on our written models. These standard performance estimation scripts provide unreliable results. There are many processes running on the device. The device processes the video stream, records the sound, applies all the previously described models to the frames, then it displays the results on screen and saves them to the database. One of the necessary processes was saving the video with sound with a positive or negative trend to make sure that mood recognition works correctly. That was a list of tasks to be running simultaneously. I had to work hard to balance the load between this process and to make sure that the message queue does not have any memory leaks. To do that, I used the following tools: OpenCV to get the frames from webcam and to put the result on the screen, Delete to find faces and calculate facial vectors, Keras to make the emotion recognition model. I've had the internet connection issue with this device all the time. This led to a loss of trend. It was necessary to change the system in such a way that it keeps everything locally, and when the access to the central server appeared, it will try to upload everything sequentially. And of course, I had to change the system as soon as possible and with minimal revision. Before the changes, the main processing daemon sent the data to the server and processed the video stream in the same thread. At first, I set up a database on the device with the same scheme as a remote one. I extract the interface of the facade. Then I made the implementation of the local facade. It was a simplified implementation of the remote facade. I successfully made a decorator, which creates a record in the queue each time the facade method is called.
There were a few dozen devices in 3 different cities in Russia at the moment of the pilot's introduction, so I needed to organize access, monitoring, and group deploying to multiple remote boxes. I made a virtual private network and generated a private key for each one. There was an OpenVPN server on our virtual machine with a web UI. I had full access to each device over our VPN. We used the Telegraph client on the device side to send the box state metrics. There were standard metrics plus the custom metrics like a queue size of the local box. I chose Capistrano for deployment to devices. Let's talk a little about the UI. Once again, the restriction of startup environment required us to move fast and get client feedback as soon as possible. Here is a list of tools I used to build UI. Ruby on Rails was used to build server-side. Code-first approach allowed me to create new features quickly. Almost at the beginning, I understood that only the server-side rendering wouldn't be enough, so I started using React.js on the front side. Then it became a separate Docker building statics for the front. I used the engines to provide static files, including video. Our first client had one camera on each establishment. The second client had many service locations within establishment. The third client had different departments across many others. One of them wanted to process only the client's emotions. Another wanted to get the staff emotions too. All of that led to a combinational explosions of ideas about reports, access, and kinds of interface organization. As a result, I built a page management system with flexible reports construct. One box can create nearly 1 million trends per month. To keep the flexibility in the report system, we had to make fast access to aggregated values of trends table. The issue was solved by calculating codes for roll-up systems. The network latency had an adverse impact on a local buffer queue. In essence, the connection channel was enough to send all of the data, but the queue was filled faster than it unloaded. There were difficulties with the dependencies between tasks in the queue, but some tasks could be done simultaneously. I managed to make a store procedure to load data by packets, thanks to great PostgreSQL JSON tools. The result of my work was a device that allows clients to flexibly customize the interface and the access structure, as well as construct a report on customer or even employee loyalty. The system can be deployed inside the security perimeters of our clients. It is undemanding of the network connection quality. That was the device the business needed. It was an overview of one of my most interesting project solution whys. Thank you for watching. I hope you enjoyed it. You may find me on social networks. All the links are down below.